All right, my friends, let's get started for part B. I probably should have mentioned in the previous video, this one is a bit more challenging than part A, but let's go ahead and jump in on it. So limit as n goes to infinity of the absolute value of, I don't always write this step that you see here that I showed in part A. I typically jump to either the step where you've defined a sub n plus 1 in terms of the actual problem you're on, or even better, I typically jump to the step where you've already flipped and multiplied. So as soon as you feel comfortable skipping a couple steps, like there's no rule against skipping some steps, as long as you show enough to really show that you know what you're talking about. So here we go. A sub n plus 1 would be n plus 1 to the n plus 1 over n plus 1 factorial. And then dividing by a sub n would be like multiplying by the reciprocal of a sub n. So that would be like multiplying by n factorial over n to the n. All right, my friends, so I've kind of jumped to this step right here in the previous problem. So, okay, now the point is to try to simplify this down and cancel out whatever you can. And for this one, it's a little trickier because of the n plus 1 to the n plus 1 and the n to the n. But the most straightforward part would be the factorials. So I'm just going to go ahead and cancel those down. So I hope it makes sense that I could kind of cancel the n factorial with n plus 1 factorial. And the only thing that would be left would be the n plus 1. And so I'm just going to kind of like cross out that exclamation point. And so hopefully that part makes sense. Okay, and then the n plus 1 that's left would cancel with n plus 1 to the n plus 1. And so this n plus 1 would cancel out one of those. So you just have n plus 1 to the n. So what would I now have? I'd have the limit as n approaches infinity of the absolute value. And you'd have n plus 1 to the n over n to the n, which you could think of as like this. And then truth is the absolute value marks are officially redundant because n is approaching infinity. So of course n is positive. So you really don't need those absolute value marks. It doesn't hurt to have them either, but you really don't need them. Okay, I'm going to go ahead and take this, I think, one more step. So this is equal to the limit as n approaches infinity of, and I'm just going to write that base there as an improper fraction. So it's not improper, sorry, it is improper as a mixed fraction. So that would equal 1 plus 1 over n to the n. Okay, and this is where a lot of folks get stuck. So if you got stuck, then, you know, don't feel bad about it. Some folks just know that this is the definition of E. So if that's you, then awesome. But for most of us, that's not us. So I'm going to put an asterisk above the equal sign. And then I'm going to remind you, because this is something that we've done in the past, I'm going to remind you how to evaluate that limit and show that it's equal to E. So how do we show that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to E? Well, notice you have a function of n raised to a function of n. And so in the past, that's been kind of a situation worth avoiding. And so we've wanted to use a logarithm and the power property of logarithms to get out of that situation. So in order to use logarithms without changing the value, we'll need an equation. So you could take the logarithm of both sides. So I'm just going to let some letter I'm not already using represent the value of this expression. And that gives me something to take the natural log of on both sides. On the right side, I'm going to go ahead and move the logarithm through the limit. So I'm taking the natural log of that part that's on the inside. And then that gives me something to use the power property on that right side. So the power property of logarithms would allow me to rewrite that as n times the natural log of the quantity 1 plus 1 over n. All right, so if you look at that, then what do we have? We have infinity for n, so you know, as n goes to infinity, and then of natural log of 1, which is 0. So we have infinity times 0. What's infinity times a number approaching 0? Well, it's indeterminate, which makes you think L'Hopital's rule, except you don't have a fraction to do derivatives on. So here's a trick. We can rewrite the right side as the natural log of 1 plus 1 over n, and then we're going to show that multiplying by n would have been like dividing by 1 over n. And then let's check, what indeterminate form do we have now? Ooh, we have 0 over 0. So right there, we have the green light to use L'Hopital's rule. So according to L'Hopital's rule, this would equal, the limit as n approaches infinity, of 1 over 1 plus 1 over n times the derivative of 1 plus 1 over n, which would be, I think, negative 1 over n squared, over the derivative of the denominator, which would be negative 1 over n squared. And then you can let the remaining n go to infinity, and you'll end up with 1. But remember that this is equal to the natural log of u, and so if the natural log of u is equal to 1, then what was u equal to? That's right, the natural log of e is equal to 1. So u must have been e. And this entire time, u was just a space holder for this limit. So therefore, the limit as n approaches infinity of 1 plus 1 over n to the n is indeed equal to e. All right, well, now that we've established that, hopefully pretty clearly, e is approximately 2.718, so it's bigger than 1. So what that means is that this series, its terms at the tail end start thinking they're geometric with a common ratio of e, so they would, the sum would definitely diverge. So the sum as n goes from 1 to infinity of n to the n over n factorial definitely diverges by the ratio test. There we go. For now, that's what you need to know about the ratio test, is just how to use it to determine whether a series converges or diverges. And so you've got an example of both here. Remember, if you get exactly 1, then the test is inconclusive and you'd have to try something else. There you go.